Good morning, students. Today in this design and analysis of algorithm subject, I'm going to discuss these topics: P, NP, NP hard and NP complete problems. So first of all, I'm going to tell you that what's the difference between polynomial and non-polynomial algorithms. There are many algorithms that can be solved in polynomial time. That means their complexity can be like big O of n square, big O of n cube, 1 or n log n. These algorithms are called polynomial time algorithms. But we have other algorithms that can't be solved in polynomial time, and their complexity is exponential. Like you may have some algorithms having the complexity 2 raised to power n or n raised to power n or n factorial. These are called your non-polynomial time algorithms. And even these are called intractable problems because as they grow large, we are unable to solve them in reasonable time. Like suppose you take fractional knapsack problem. Okay, the complexity of that is in the range of 2 raised to power n. So once the value of n becomes larger, like 15 or 16, we won't be able to run them in our computers or in our laptops. So we should have some solution for all these types of problems. Okay, next. Okay, what are polynomial time algorithms? Are some problems solvable in polynomial time? Yes, we have already done many algorithms like sorting, searching. All these problems are your polynomial time algorithms. Next, are all problems solvable in polynomial time? No, we have many problems that can't be solved in polynomial time. Like here, we have Turing's halting problem, or you take knapsack problem, Hamiltonian cycle, traveling salesman. All these problems can't be solved in polynomial time. And this is very important that all the problems that we can't solve in polynomial time, they are either optimization or decision problems. Okay, optimization problems means for which the output we have to minimize or maximize something, and decision problems in which the output will be either 0 or 1. Now, what's the difference between optimization problems and decision problems? Like I have already told you, an optimization problem is one which will ask what is the optimal solution to the problem X. Optimal solution means in that they have to maximize or minimize something. Like if we take 0, 1 knapsack and fractional knapsack, in these problems we have to maximize the profit. And in minimum spanning tree, we need to find out a tree from a graph such that the sum of all the edges should be minimum 1. That means we are going to maximize or minimize something. And what are decision problems? A decision problem is one with yes or no answer. That means the output of that should be either 0 or 1. Like for minimum spanning tree, what is the optimization problem? Find out a spanning tree from a graph such that the sum of all the edges should be minimum. Now the same problem can be converted into a decision problem. And what would be the decision problem for this? Does a graph G have a MST of weight less than equal to W? So that will become a decision problem because the answer of this will be either yes or no. If the weight of this tree can be less than equal to W, then answer will be yes. Otherwise, your answer will be no. Now, an optimization problem tries to find an optimal solution, and a decision problem tries to find an answer with yes or no. Many problems will have decision and optimization versions, like you take traveling salesman problem. Now, if we have to state the optimization problem for this one, what would be that? It would be that find out the route, like a traveling salesman is starting from a city. He is going to all the cities, he is traveling all the cities only once and coming back to the original one. but the total weight of all the edges should be minimum. So that is your optimization. Now, what is the decision problem? Is there any cycle of weight less than equal to k? Now, what would be the answer of this? If the cycle can be less than equal to k, answer would be yes, otherwise it would be no. So some problems are decidable but intractable because as they grow large, we are unable to solve them in reasonable time. That means like you take this traveling salesman problem. The complexity of that is in the order of 2 raised to power n. So we won't be able to solve them as the value of n becomes large. But is there a polynomial time algorithm that solves the problem? So we have to see this thing. Do we have any polynomial time algorithm for all these problems? All these problems that can't be solved in polynomial time by using deterministic algorithms. Okay, next we have what's the meaning of P? Okay, before this, I need to tell you that what's the meaning of these deterministic algorithms. A deterministic algorithm is one that always computes the correct answer, or we can say in which each and every function is going to have the unique value. Each function in that algorithm is going to give us the answer that is unique. It won't give more than one answer. So what is P? P stands for polynomial time. So it will be a class. Class means it will be a group of all the decision problems that have polynomial time deterministic algorithms. Like you can see all the sorting, searching algorithms that we have already done. All these are your P problems. Or any decision problem like we have already done that can be solved by using deterministic algorithms, those are called your P problems. So they are solvable in big O of Pn time. What is Pn? Polynomial time. Like Pn can be n, it can be n square, it can be n log n. So if the complexity of that algorithm is big O of something polynomial, then those decision problems would be called P problems. So some problems that come under this P are like fractional knapsack, MSP, sorting, all these are your P. Next is NP. Okay, now what was the deterministic algorithms? Next we have non-deterministic algorithms. Now what are non-deterministic algorithms? These are the algorithms in which a function may have more than one output. It's not going to give you the unique value, it's going to give you more than one value. So these non-deterministic algorithms we can't run in our computer that we have been using to run other algorithms. So we need to assume these are just theoretical concepts, research-based concepts. So we need to just think about a non-deterministic computer in which you are going to have the parallelism. Like you can assume that whenever your algorithm is being run, n copies will be made by that non-deterministic algorithm, and all those n copies will be computed in parallel. Okay, so what are NP? N stands for non-deterministic and here P stands for polynomial. So it is a group of all the decision problems that can be solved in P means polynomial time on non-deterministic machines or by using non-deterministic algorithms. So all those problems are called non-deterministic polynomial time problems and P non-deterministic polynomial time. But these should be your decision problems. So sample problems in NP like fractional knapsack, traveling salesman, Hamiltonian cycle, graph coloring, satisfiability problem. So I'm going to discuss this one, satisfiability problem. All these problems will come under NP. Now this problem is very important because all NP problems, they are computationally related to each other. Computationally related to each other means if you can solve one problem, then you can solve the other problem also. But all these things will start with this satisfiability. Okay, what is that satisfiability? You have already done this thing. This type of expression is called Boolean expression. And in this, I'm going to have four variables. So given a Boolean expression on n variables, can we assign values such that expression is true? That means you need to assign some values like zeros or ones to all these variables, and we need to find out whether the output of this is true or false. So again, this is a decision problem because the output of this is either 0 or 1. Now, if I will take these four variables, what are the different combinations possible? What are the different inputs that I need to try for this? There would be 2 raised to power 4, like 16 values I need to check. So for this problem, it's fine that we can implement this by using deterministic algorithms on deterministic computer. But once the value of variables becomes very large, like if it is 14, 15, 16, we won't be able to run this algorithm on our computer. That means I won't be able to find out the output of this expression. So the complexity of this is not polynomial. The complexity of this is non-polynomial. It is in the range of 2 raised to power n. Because if there are 4 variables, I'm trying 2 raised to power 4 combination. If variables are 5, I need to try all the 2 raised to power 5. If it is 10, then I need to try 2 raised to power 10 combinations. So there is no polynomial time algorithm for this. So SAT is a problem. SAT stands for satisfiability. It is a problem for which we know no polynomial time algorithm. So we have no proof that it is intractable, no proof that there cannot be polynomial time algorithm. That means we can have polynomial time algorithm, but that won't be deterministic one. That would be non-deterministic. So here I have written deterministic as well as non-deterministic algorithm. First, this one is your deterministic algorithm. Like while there are untried interpretations. Interpretations means inputs. Like suppose if there are 4 variables, the first input is 0, 0, 0, 0. Another input can be 0, 0, 0, 1. Then it can be 0, 0, 1, 0. So we need to try all the inputs. If I satisfies this W, then return yes, otherwise we will return no. So here we need to try all the interpretations, all the inputs. So how many inputs are there? 2 raised to power n. That means the complexity of this is exponential. This deterministic algorithm can't be solved in polynomial time. Now, what is the non-deterministic algorithm for SAT? Non-deterministic algorithm is that for each distinct symbol in W, W is the set of all the inputs, set of all the variables. For each prepositional symbol in W, in non-deterministic algorithm, we can have this function choose, then we can have failure and success functions. So in non-deterministic now, you need to think that your computer, non-deterministic computer, will make n copies of this algorithm and each copy will be run in parallel. So all the inputs will be tried on your expression in parallel. So it is selecting 0, 1. If V is 0, we are assigning false to the prepositional symbol, else we are assigning true to the prepositional symbol. So all the copies are being run in parallel. So if in any case we are getting the success, then that means the expression is true for that, otherwise expression is false. So This algorithm can be solved in polynomial time as all the copies are being run in parallel, so we are getting the output in polynomial time, but we don't have deterministic algorithm. This algorithm is your non-deterministic. Okay, so SAT is in NP. NP means it can be solved in polynomial time, but by using non-deterministic algorithm. So we will call that this is the first problem that we have discussed that is in NP. That is a NP problem. Okay, next, before going to NP hard and NP complete, I will tell you that what is the meaning of reducibility. Suppose I have two algorithms, two problems, L1 and L2. Now L1 can be reduced to L2 in polynomial time. If we have a polynomial time algorithm for L2, then we can also solve L1 in polynomial time. That means L1 can be reduced to L2. Suppose already you are having the polynomial time algorithm for this L2. Then by using that algorithm, we can solve L1 also. That means this can be reduced to this one. This is called your reducibility problem. Now I can define that what are NP hard problems. Now suppose I'm taking a decision problem PI and I want to prove that that PI is NP hard. Now it would be NP hard if every problem in NP is polynomial time reducible to PI. Let's suppose you are having, I want to check that PI is NP hard. So I am going to take PJ. Suppose PJ belongs to NP. Like I have already proved that satisfiability problem is NP. Now, similarly, there are many problems that are NP problems. Now, if I can prove that all those problems that are already in NP that are reducible to PI in polynomial time, then PI will be NP hard. Okay, but for this, it doesn't require PI to be in NP. PI can be non-NP problems. So that means PI is as hard as all the problems in NP because all those problems can be reduced to PI, or by using the solution of PI you can solve all those problems. So this is as hard, as difficult as all other problems in NP. So if PI can be solved in polynomial time, then all the problems in NP can be solved. All the problems in NP can be solved. So again I'm repeating this. PI is called NP hard if all the problems in NP can be reduced to PI in polynomial time. That means if PI can be solved in polynomial time using any non-deterministic algorithm, then all the problems in NP can be solved in polynomial time. Okay, but another thing is that it doesn't require PI to be in NP. Next we have NP complete problem. Now decision problem PI is NP complete. First condition is that it should be NP hard. Other thing is that it should be NP. Like in NP hard, it doesn't require the PI to be NP. But in NP complete, that problem should be in NP. So these two conditions we need to prove for a problem to be in NP complete. So PI is NP complete if PI is NP hard and PI belongs to NP. So we can say that PI is one of the hardest problem in NP. This is just a review of what is P problems and NP, and we know that okay, there is a relationship between all these P, NP, NP hard and NP complete. First, just consider this circle. This belongs to all the NP problems, and this smaller one that belongs to the P problems. So here we have written that P is a subset of NP. Now what's the meaning of that? Now, previously in the past, some of the P problems may belong to NP. We can assume that in past we didn't have any deterministic algorithm for these problems. But with time, we got the solutions for all these problems. So we can say that previously P belongs to this category NP. So P is a subset of NP problems. Now, what is NP hard problems? In NP hard, it doesn't require NP hard problems to belong to this NP. So this thing that is white one that belongs to your NP hard. But what is the condition for NP complete? That should belong to first NP. So within this circle, those algorithms, those problems will come. And the other thing is that that should also belong to NP problem. That should be NP. So this one. So these problems represent NP complete. So that is the relationship between P, NP, NP hard and NP complete. So that's all for this lecture. In my next lecture, I will take some problems and we will prove that whether those are NP hard or NP complete.